afternoon. I am Renu Sharma, Assistant Professor, EC Department. Today I am going to start with the next unit for the subject, that is wireless and mobile communication, and the topic of today's lecture is wireless channel model. So whenever we are talking about wireless communication, which means there is no physical connection has been set up between the transmitter and receiver. We are just going to broadcast the information from the transmitter to the receiver. So for that purpose, we have to model the channel depending on various probability density functions, and these functions are based on various distributions. Like first one is Rayleigh distribution, RICIan distribution, then there is a fading channel is also there, Nakagami fading channel, Okumura and Hata model channel is there. So these are the basic models that we are going to discuss in today's lecture, so that we can model the channel for the wireless communication. So first we'll begin with what is wireless channel modeling, that is propagation models. So a radio propagation model, why we are calling radio propagation model, because whenever information is sent, it is sent in radio frequency range. So it is also known as radio wave propagation model, or radio frequency propagation model is an empirical mathematical formulation for the characterization of radio wave propagation as a function of frequency, distance and other conditions. So whenever we are talking about propagation model, it is based on empirical mathematical formulation, which means that it is on the basis of measurements that we are taking. Like if I am considering the Rayleigh distribution, then Rayleigh distribution is considered and it is designed, that particular PDF is used to design the channel. Then some calculations are made. How the calculations are made? It has a set value of PDF. We have to change the input value, and then using that PDF, that is a formula, then we have to calculate the different output. So that is the main idea behind the empirical mathematical model. There is also another model, that is a statistical model, which is also based on the distribution, and it is based on the statistics only. Then it is created with the goal of formalizing the way radio waves are propagated from one place to another. Such models typically predict the path loss along a link or the effective coverage area of a transmitter. Means when we are designing any channel, we have to see various parameters. We have to keep in mind various parameters, like multipath propagation will take place. That is obvious reason, because there is no exact line of sight exists between the transmitter and receiver in urban areas especially. So various propagation effects will going to affect the quality of the signal, and it will also affect the channel modeling characterization. Like scattering will be there, diffraction will be there, reflection and refraction. These are the main 4 points, and other points also exist that will going to change the modeling of the channel. So as the path loss encountered along any radio link serves as the dominant factor for characterization of propagation for the link, the radio propagation model typically focus on realization of the path loss. So path loss also plays a very important role when we are calculating the Friss formula for path loss model, that is PR is equals to PT GT GR lambda square upon 4 pi R square, where R is the radius of the particular cell, and that is the distance, and PR is received power, PT is transmitted power, then GT is gain of the transmitter antenna, GR is the gain of the receiver antenna. So these are the various factors that we have to consider while designing the channel. So as a result, different models exist for different types of radio communication link with under different conditions. For any model, the collection of data has to be sufficiently large to provide the enough likeliness to all kind of situations that can happen in that particular scenario. So larger number of parameters which are calculated, or larger number of data which has collected for the purpose of calculation of various parameters, it has to be done so that the effective result or the proper result will be achieved by using different communication channel models. Then these are the propagation models which are used, like different models have been developed to meet the need of realizing the propagation behavior in different conditions. Like the type of radio propagation include, first one is for the free space attenuation, that is free space path loss model. Now the formula for this free space path loss model is the Friis formula. And in this condition, I have told you in the previous slide also, the received power will be given as PT GT GR lambda square upon 4 pi r square. So 4 pi r upon lambda whole square, it is nothing, it is the path loss, and we have to calculate it in terms of decibels. Another formula for free space attenuation is dipole field strength in free space. Friis transmission equation is there. This is the Friis equation. Then models for outdoor and indoor. So there are various models, like for the outdoor it is dependent on the terrain models, that is AKGEC model 2, Ray ground reflection model, ITU International Telecommunication Union terrain model. Then city models are Okumura model, Hata model for urban areas, Hata model for suburban areas, and Hata model for open areas. Open areas can also be considered as rural areas, because in between the transmitter and receiver there is very less density of population exists, and secondly no high rise buildings are there, no other obstacles exist between the transmitter and receiver. So that's why I have considered as rural model. Another is cost Hata model. Then models for the indoor attenuation are log distance path loss model and ITU model for indoor attenuation. So these are the various models, and if you can visualize that these are dependent on whether it is considered for outdoor application, whether it is considered for indoor application, secondly whether it will going to cover urban area or it will going to cover the rural area. So indirectly it is related to population only. So the first one is the additive wide Gaussian noise. In wireless communication or any mobile communication, mobile is wireless communication or analog communication, whichever noise we consider for the mathematical calculation, that is AWGN noise, that is additive wide Gaussian noise, and in short form it is written as AWGN, that is additive wide Gaussian noise. So the AWGN channel model can be characterized as follow. Like the noise is additive in nature because it is written over here. So the model which is designed is like this one, simplest model I am considering. This is the transmitted signal, this is the noise, this is the received signal, then this is the modulo 2 addition, so you can also say that this is the addition of the two signals, that is the input signal, it is also known as, this is also known as the input signal noise, and this is the signal that has to be transmitted. So this is how the model is designed, a very simplest kind of model. So the noise is additive in nature, that's why we are considering additive wide Gaussian noise. Secondly, the noise is white, which means it contains all the frequency components. Thirdly, its power spectral density, that is PST, is constant, and it can be considered as one-sided, or if it is considered two-sided, then it will be extended from -infinity to infinity, and its amplitude will be n0 by 2. So that is the power spectral density of white noise, which will extend from -infinity to infinity. So if you want to use it for any mathematical application, mathematical calculation, then you can pass this particular white noise with a filter which will going to band limit this particular noise. So that will be band limited, let's say from -f1 to +f1. So that's why it will be considered as, that will be band limited to a particular range of frequency. Now next is noise samples have a Gaussian distribution. The Gaussian PDF is given by variance sigma square, which is given by this equation. Px will be is equals to 1 upon under root 2 pi sigma square e to the power minus x minus m whole square upon 2 sigma square, where m is nothing, it is the mean of random variable x, and sigma square is the variance. So that this is very common Gaussian function distribution. Sigma square, it is nothing, it is the variance, m is the mean. So this is how you have to calculate the additive white Gaussian noise concept. Now next is, it is a very good model for physical reality as long as the thermal noise at the receiver. So another name for the white noise is thermal noise. It is also known as thermal noise. It is also known as Johnson noise. So all are same thing. Mostly it is called as white noise or additive white Gaussian noise. Then this is the concept of white noise. Now you can see over here that if it is extended from minus infinity to infinity, amplitude is n0 by 2. You can band limit to a particular duration, and if it is, this is two-sided because it will extend from minus infinity to infinity, and it is nothing, it is one-sided concept which will be extend from 0 to a w. So the bandwidth of this will be w and bandwidth of this one will also be w because it will be two-sided concept. Now this is the third one, is the typical Gaussian distribution with 0 mean, and S is the standard deviation. Now you can see that at 0 origin its amplitude is maximum and it will be reduced when we move towards infinity. So that's why this is also known as normal distribution, this is also known as Gaussian distribution. Now next is, this is an impulse is transmitted on a stationary channel, then at the receiver multiple delayed versions of impulses will be received at different instants of time due to multipath. So basically what happened in multipath propagation, since let me show you with a diagram. Let's say this is the transmitter, this is one node N1, this is the receiver and node N2. Okay, we want to transmit the information from this point to this point due with the help of wireless communication. So it may be possible that there exists some antenna, there exists a tree, there exists a building. So there will be multipath propagation that can happen like this one. This is the possibility, maybe 2 hops will be there, maybe 3 hops will be there, maybe single hop, but there is no, means there is very less probability that the signal will directly deliver to receiver, means there will be no multipath propagation. So since it will going to follow 2-3 paths because it is a multipath propagation, then all the signals which are received will be added at the receiver side. That's why it is written over here that it will be a delayed version of impulses will be received at different instants of time due to multipath. So due to multipath, let's say 3 different signals will be received, all will be delayed version, all will be received at different instant of time, and all will have their own energy because it will going to reduce as the number of hops will be increased or intermediate nodes will be increased, then the strength of the signal will definitely going to reduce. So these impulses are non-correlated and with reducing amplitudes with time. So this is the main diagram behind this autoregressive model for a channel. You can see the delayed version of different signals will be received. Now next is conceptually they are just like delayed samples. If we want to draw a mathematical model, we want to analyze that particular in terms of mathematical model. So hence a difference equation with coefficient values can be used to represent this concept, which is the equation for a finite impulse response. So there are 2 types of responses, finite impulse response and infinite impulse response, FIIR and IIR filter. So we are considering the finite impulse response, which can be modeled using this equation, that is Rn is equals to W0 Sn plus W1 Sn minus 1 plus W2 Sn minus 2. So what are these W? These are the weights, W1, W0, W1, W2. So how many numbers of signal you receive? You will use that many number of weights. These are multiplied by different delayed version of single transmitted signal. Like this is delayed by 1 unit, this is delayed by 2 units, this is not delayed. So the channel model for a time varying channel can be approximated by the autoregressive model, which is shown in the previous slide. This one, this is the autoregressive model. You can see that this is not delayed version, this is delayed by 1 unit, then these are delayed by n number of units. So this is the channel model, that Hn plus 1 is equals to W1 Hn plus W2 Hn minus 1 plus up to Wn Hn minus n plus Wn. So this is the initial version. Now where Ws are the weights or the coefficient values to estimate the channel model. Now next is the received time domain signal, that is denoted by Rn, is a function of transmitted signal Sn, the estimated channel transfer function, and AWGN, that is denoted by Wn. So this is how the received signal will be modeled, which is Rn is equals to Sn. It will be convolved with HEN, that is the impulse response of the particular filter, and added with the noise. So this is how you are going to model a particular channel. Now next is multipath fading channel modeling. Since we are discussing this wireless channel model, and due to multipath the signal strength will going to reduce, so that's why it is also known as fading. Fading is another concept. So for the flat fading, it is found that the multipath can be modeled by using Rayleigh statistics or RICIan statistics. These are the different two probability density functions that we consider. With the Rayleigh stats, the PDF of this random variable R can be written as this. This is a well-known formula for this Rayleigh distribution, that is the probability density function. PR will be equals to R upon sigma square. Sigma square is the variance, e to the power minus R square upon 2 sigma square. So R is nothing, it is the random variable. Sigma square is nothing, it is the variance of that particular system. Next is Rayleigh fading. So since we have seen the equation for the Rayleigh distribution, we have to see that how for different values of sigma, what will be the curve of that particular distribution. So Rayleigh fading is viewed as reasonable model for urban environments where there are many objects in the environment that scatter the radio signal before it arrives at the receiver. So this is the distribution. You can see over here that as sigma values increased, the curve will be extend towards the origin. So this is how, and at sigma is equals to 1, this will be the curve of Rayleigh distribution. Now next is Rayleigh fading model. You can see over here that this is the fading duration, this is the non-fade duration for the Rayleigh distribution. This is the probability density function, and this is for the Rayleigh one, that is Rayleigh sample of a Rayleigh fading. Then this is PDF, this one is the PDF. C is the variations in the Rayleigh with the different values of sigma. You can see I have shown up to this point, sigma is equals to 1. When sigma is 0.5, means when it is less than 1, it will show a highest peak. Then variations in Rayleigh CDF with change in standard deviation or mean. So this is the CDF. Now next is multipath Rayleigh fading signals. So two extreme cases are distinguished, like first one is the coherent accumulation and second one is the incoherent addition. So what is coherent and incoherent? Whenever we are talking about communication in case of modulation, Carrier signal has to be used at the transmitter side and as well as the receiver side also. When both the carrier signals are having the same phase and frequency, then coherent and non-coherent is distinguished. In case of coherent, it should have same phase and frequency. In case of non-coherent, it should have different phase and frequency. So coherent cumulation, this is also known as phasor cumulation. It occurs if during the observation interval, the fluctuation of the phases caused by the modulating signals are sufficiently small and the carrier frequencies of the signals are exactly equal, which means it has the same phase and frequency as it is used at the transmitter side. In case of incoherent addition, this is also known as power addition, and if the phases of each of the individual signals are substantially fluctuate due to mutually independent modulation, the signals add incoherently. So this is what incoherent addition is all about. Now next is multipath, multiple Rayleigh fading signals. Since multipath propagation will be there and all will follow the Rayleigh distribution, so the joint signal behaves as a Rayleigh phasor with Gaussian in phase and quadrature phase components. The local mean power is equal to the sum of local mean powers of the individual signals. So which is shown over here. This is the quadrature phase component, this is the in phase component. These are the reflected waveforms as you can see over here, and this is the resultant of all these waves which are received over here. So this is how this resultant wave is calculated. This is the in phase component equation, that is IT is equals to summation n is from 1 to capital N, alpha n cos is I plus phi n, and QT will be the quadrature phase component. This is quadrature phase component, this is in phase component. In quadrature phase it is n is equals to 1 to n alpha n into sine xi by phi n. So in case of quadrature phase, we are considering the sine component, which is 90-degree phase shifted version of cos sine, and cosine is the signal which is generated by the local oscillator as a carrier signal. Now next we will move to RICIAN fading, which will use the region distribution. So if the environment is such that in addition to the scattering, there is a strongly dominant signal seen at the receiver side, usually caused by the line of sight transmission. So when a line of sight is possible between the transmitter and receiver, then the strong signal, the quality of the signal is strong, that whatever you have transmitted you will receive exactly the same, which is not practically possible due to the effect of noise, due to the effect of atmospheric propagation. So then the mean of the random process will no longer be 0. So varying instead around the power level, the dominant path is shown over here, which is the RICIAN fading. So such a situation may be better modeled as the RICIAN fading. So this is the RICIAN distribution, the like one we have seen in the Rayleigh distribution. So this is the formula for the RICIAN probability density function, where sigma is the standard deviation, alpha is the amplitude of the direct signal, I naught x is the zero order Bessel function of first kind. Then this is PDF PR denoted over here, which is extended from 0 to R. Then this is 0 to 0.6. So this is how it is shown over here. This is alpha is equals to 0, 1, 2, 3. So for the different values of alpha, this Rayleigh distribution looks like. Then this is the RICIAN PDF envelope at the different standard deviation values, like you can see over here. Now next is the RICIAN PDF is already described mathematically in the previous slide. Then the K factor is defined as the ratio of the signal power in the dominant component and the scattered power. So when K is a factor, this is the role of factor, then K can be 0, it can be infinity. If it is 0, then the channel is a Rayleigh channel, and if it is infinity, then the channel will be a additive wide Gaussian noise channel, which means that the denominator is 0 in that case. So the variation of the Doppler spectrum in terms of spectral density SF is given by this equation, that is SF is tends towards this particular formula. Now why we are considering this Doppler spectrum? Because since we are talking about wireless communication, then the transmitter and receiver both are moving in nature most of the time, and there is a non-wired or wireless channel has been set up between the transmitter and receiver. So which means when the receiver is moving in nature, let's say it is moving towards the transmitter, there will be two possibilities: either it is moving towards the transmitter or it is moving away from the transmitter. If it is moving towards the transmitter, then the frequency will be added. The reverse frequency, let's say this is the transmitter side and this is the receiver side. If it is moving towards the receiver, then the round off frequency will be doubled, and if it is moving away from the transmitter, then the round off frequency will be reduced, means it will be subtracted. So whatever signal we will receive, it will going to decide on the basis of that whether receiver is moving towards the transmitter or it is moving away from the transmitter. So this is all about today's lecture, which is about the wireless channel modeling, where we have discussed different models like Rayleigh distribution model, then RICIAN distribution model. So thank you.